Please.
Okay, thank you very much. Good afternoon. I would like to say thank you to Dr. Asma and the chairman for this last-minute arrangement. But I think that my talk fits well even in this session. So, well, the title says almost all. I think that we may agree that there is a bottleneck in the panorama of communication systems for CubeSat, and I will make a small proposal to enhance communications, and I will display some steps of the design and optimization process, and then we'll conclude with some remarks. So this is a quick view of how fast the CubeSats were launched in the last few years, in the last couple of years, well, the top line shows the count of systems of radios that use UHF frequencies, and at the bottom, the red one shows the count of telecommunication systems that use frequencies above the gigahertz. So, and these data are of course available from the CubeSat communication tables of Mr. Kaufman's. Why there is such a difference in the frequencies that are used? Of course, many of the institutions that launched their first CubeSat prefer to use low-tech radios because they are more reliable and often more affordable. But the usage of low frequencies has its drawbacks, which are the need of big dishes, large altitudes of the antenna at the ground station. On the satellite itself, very high power is needed to transmit a signal, and the channel has an overall low capacity. Instead, the use of higher frequencies above the gigahertz allow the reduction of the size of the antennas, both on the space segment and on the Earth segment. Allow for an increase in power efficiency, principally on the satellite, on the spacecraft, and makes higher capacities more achievable. And there is a little fact that the data rate can increase as the frequency increases, if and only if on both ends of the communications directive antennas are used. So my proposal is to adopt an array antenna on the CubeSat, which is flat, it's thin, so it can be put on one of the sides of the spacecraft, and it's also light. This was done in a three-step design process. So first of all, I choose the basic element of the array, and this is a very simple antenna. It's a rectangular microstrip patch antenna, and it's linearly polarized. However, this element, this kind of an antenna, has its drawbacks because it has good radiation performance in a very narrow bandwidth. So the idea is to enhance the performance over a larger bandwidth using this particular arrangement, which is the sequential rotation technique. Once this subarray is obtained, it can be arranged in a larger array that gives more gain to the overall radiating structure. The simulation and the optimization were carried out using CST Microwave Studio and Mode Frontier as the optimization tool. Starting with the single element design, the known parameters the engineer choose are the substrate dielectric constant, the substrate thickness, and the operational frequency. And the results are the size, the dimensions of the antenna, the length and the width. But sometimes the standard approach gives results that are outside the desired range, so an optimization is needed. And this is this plot shows the progress of the optimization performed with a genetic algorithm. On the horizontal axis, there is the objective on the resonant frequency, which was said to be within the 37 and 37.5 gigahertz, and on the vertical axis there is the another objective of the antenna matching. And well, this diagram shows the evolution of the genetic algorithms with well, it's a stochastic. It's a stochastic algorithm, and there are two main peaks, and the last one, the red one, the more red one, is are the final designs that have been evaluated. After the basic element design, there was the optimization of the subarray, and for the subarray, the input parameters to be optimized were the position of the elements along the x-axis and the y-axis according to the reference system shown. And the observed outputs were the actual ratio, which is the main parameter that gives an information of the polarization quality, the maximum directivity, and the side lobe levels. And the objectives were an actual ratio in the B equal to 0 to maximize the directivity and to minimize the side lobe levels. And this is the result of the subarray optimization, which shows a very good actual ratio along all the bands selected for the antenna operation. And usually an antenna is considered circularly polarized when the actual ratio is less than 3 dB, and here the actual ratio is less or equal to 0.2 dB. So this was a very good result. Then after designing the subarray, it can be many subarrays can be arranged in a grid. The size of the subarray compared to the size of a CubeSat makes possible an arrangement of 64 subarrays for a total of 256 small antennas. This array is a uniform array, which means that the distance between different elements is constant, but it is constant also the amplitude and the phase of the signal feeding the antennas. And the result is shown. This is the radiation pattern of the complete array. And well, in the center there is the propagation direction, and there is a maximum directivity of 30 dB, which is a very good figure compared to the requirements imposed to the antenna. And also the side lobe levels is quite good because it is very similar to the theoretical results for a uniform array. Summing up what I've said, the CubeSat communication subsystem needs have been assessed, and a solution consisting of a uniform array antenna have been proposed. And this array, I share some details about the design and optimization process with the genetic algorithms made available by Frontier. And also at the end of the process, requirement satisfaction was verified. What we are going to do next is to perform a robust optimization in order to account for uncertainties introduced by the manufacturing process. Then there is the design of the feeding network, which will be an important step that will characterize the antenna performance, and also improve the performances of the complete array, and specifically it is our intent to improve the side lobe levels. And and in this circumstance there are two paths available. One is to use the stochastic optimization again, and the other is to use the other deterministic methods. Deterministic methods can be preferred because due to the large number of radiating elements, simulations can take very long. And that's all.
Thank you very much. Any questions? The back there.
I was just wondering if you have any estimate on the size of the feeding network.
The feeding network is supposed to be on the back of the panel, but it's a design choice. It can be a microstrip feeding network on the same surface where the microstrips, where the patches are printed. It can also be placed on the other side, on the opposite side, because patch antennas can be manufactured with common PCB processes. So it can be a single layer or a single phase or a double phase design.
Okay, thank you. Anyone else? Okay, join me. Thank you.